Part B, where we're stepping up, okay? So I'm going to do it in long form here, which is that I'm going to use the formula, and I'm going to use it, now, how many times? How many applications, how many parabolas am I going to have if I've got 6 sub-intervals? I'm going to have 3, because it's n on 2, if you like, okay? So as I start to write this out, I'm going to write it in full form. So it's going to be h on 3, and then I've got, now, my upper and lower boundaries are still the same, right? Still 1 and 2, okay? But what happens in between changes, right? So before I write out the rest of this, let's think about this. N is 6, right? That's how many subintervals I got. So what is h? How do I work out h again? I take that distance, right? Which is b minus a, which is 1 in this case. And then I divide by, what am I dividing by?
The number of...
I divide by however many intervals I have, right? So in this case, I divided by 2, because I had 2 subintervals. Now that I've got 6, I'm going to divide by 6. Okay? So they're quite small, right? So I'm going to get pretty good accuracy here, yeah? All right, if h is 1 on 6, now I have to use that to work out what all my function values are. Okay? Now that was super easy. In this case, I only had 3, right? But what are my function values here? Well, my values will be, I'll start at 1, and then I go forward 1 perpendicular height, right? So I guess the next one will be 7/6, and then the next one will be 8/6, and 9/6, and all the way up until I get to the last one, the upper boundary. Okay? You happy with that so far? So that's a bit gross, but thankfully the function is not that bad. Okay? So now I'm going to start to put this into my formula. Okay? So I'm going to have the first parabola, right, is made up of these first 3 values. Yeah? So I'm going to go f of 1, 4 lots of the next one, and f of that last one to end out my parabola. Okay? 1, 2, 3, I'm done. Okay? Now, then I can go on to the next parabola, which is this one. 1, 2, 3 values. See it? See how I'm piecing it together? So this is going to be plus, still the same perpendicular height, right? F of, now there's my 8 on 6, which doubles up. 4 lots of that one. And then 1 lot of this one. Okay. Sorry, this is starting to get a little bit cramped. Didn't leave myself enough space. That's the second parabola, and here is the third one. Okay? You see how I'm just taking these values one at a time. So h on 3, f of 10 on 6 is my first one, 4 lots of the middle one, and 1 of the last one. I'm done. Okay? So this method, like I said,
combine them into a gigantic problem.
So I will in a second, yeah. So this method, right, obviously takes significantly longer to write, okay? But if you, after doing a few of these exercises, right, if you're finding that you're getting answers just numerically wrong because you're messing up the method, okay, that's a sign that you should stop using the compressed version, the 1 4 2 4 2, 2 4 1. You should stop using that one and go back to actually doing it from scratch, okay, to reduce the number of errors you're introducing. Okay, so now I'm going to start to evaluate some of my numbers, yeah? H on 3, let's factor it out. So that's 1 on 18, yeah? Okay, f of 1 is still just 1. Now I've got 4 lots of, and my function is just take the reciprocal, right? So that's nice and easy. 4 lots of 6 on 7. 2 lots of 6 on 8, which is 3/4. 4 lots of 6 on 9, which is 2/3. 2 lots of, where am I up to? Here. 6 on 10, which is 3/5. Where am I up to? Here. 4 lots of 6 on 11, and then I finish. Okay. Yeah, that looks a bit gross, right? Thank God for integration. But you work it out. Actually, I can't remember what this fraction is off the top of my head, but someone can tell me once they get there.
Calculated doesn't give me a fraction.
Okay, what decimal does it give you?
6, 9, 3, 1, 6, 3,
So, 0 point.
0.69416979.
I lost it. Is that okay? Is that, are those 6, 9 there?
I think so.
Yeah? Okay, great. Now, since we've got that as a decimal, can we get this as a decimal as well?
Why do we have to keep using squiggly equals sign?
Because,
because
what I've started with, right, I've defined the left-hand side as this, this integral, right? So this integral is equal to that, but I'm not working out the integral here, I'm working out an approximation to the integral. I did get asked once, someone said, hey, you know what, this is approximately equals, fine. But when I go from this line to this line, aren't those two equal? So shouldn't I change to an equal sign? And the answer is no,
because you're not saying it's equal to the last line, you're
that's
saying
right.
it's equal to the other
I'm
hand.
saying left-hand side is right-hand side. Exactly right. Okay, sorry. Can someone give me this as a decimal?
0.694.
Thank you. Okay, right. So that's how you approach this question, right? If you like, you can go straight to this form. That's fine. But like I said, the more shortcuts you use, the more error prone it is. So if you're making errors, stop using the shortcuts until you don't make the errors anymore. Okay, now I picked the same function, I think, that we used to practice trapezoidal rule on, okay? So let's just take a moment to step back and appreciate how awesome Riemann's work was, right? What is this area actually equal to? Because we can work it out, right? From 1 to 2, it's going to be log x with those boundaries, okay? So it's log 2 minus log 1, which is 0. So what's log 2? 147. Okay. So you can see, because we did Simpson's rule right, we were getting pretty close, right? Well, how many is that? That's 4 decimal places, which is not bad, right? But then you look at this amount of work versus this amount of work, and yeah, that's why integration is pretty cool.